I'm not gonna use any earphones because otherwise your voices will not be recorded. I'm sure there's an option on Zoom that would take your voices through my microphone, my earphones, but I don't have it on for the moment. So what we're gonna do is the following. Before we start projectile motion, probably if you want, I can write our plan on a blank paper. Hello, Magali. Okay.
Hello.
Hi. So the plan for today is one, I need to check if you're okay with lab number 2. So lab number 2, any questions? This is the first thing we're gonna do. And then we're gonna cover the theory for lab 3. The reason why we're covering the theory for lab 3 is because I assume it's a little bit challenging and a bit advanced. So I thought it will be it's gonna be a good time for us to finish it before we meet next Monday, hopefully, so we can do the experiment. The experiment is heavy, the experiment is long a bit, it's very messy, and it's very loud. We have 3 big devices and we're gonna launch those balls and they're loud. It's gonna be really a headache for you. So let's really focus on the theory now to be able to apply it directly next time I see you. All right. And you know, I'm not allowed on campus for this week, and I didn't want us to have a week off and to lose this time. Before we continue, let me put the participants here. I just need to see how many we are. I was expecting 12 participants and it's not going to happen.
There are some students with no electricity, they can't join.
Yes, thank you for informing me. Yes, I think next time we have this issue, probably I'm going to ask Ms. Jinan to sign us in from the lab. So you're going to use the lab and the projector on the screen to be able to communicate with me. Do you think it's a good idea?
Yes, I think so.
Yeah. Anyway, I will never miss the lab unless there's a major issue like today, you know. All right, so now the floor is yours. Anything you would like to talk about concerning lab 2? Did you submit the lab? Are you having difficulties?
No, it was easy. I submitted.
Okay, anybody has an issue? Lab 2 is fine. All right, I have our Blackboard open. It's here. Let me go over it with you. This is not Blackboard, this is it. And these are my courses, mechanics lab. I've graded some of your lab 1. If you posted your lab 1 a bit late, I did not grade it yet. Yes. Okay, so let me see who's on, who's not. And probably it will be a good reminder for you. Some students did not submit classwork too. Lab 1, as you can see, some are not graded yet. Lab 2, excellent submission. So the students that are usually submitting the work on time, they all submitted lab 2. All right, so I can see you have no issue. By the way, lab 2 is easy. I was only concerned with some technical stuff, like if you know how to use Excel, how to find the slope, and apparently it was a good practice for you. Am I right?
Yes.
All right. Now let's start with lab 3. I prepared a presentation for us just to make it a bit quick, but the presentation is basically empty. We're going to fill it together. Projectile motion. This is your lab 3. I'm going to send it to you. I'm going to edit on it. And since I'm recording the session, probably you can watch it again if you want. Okay. Projectile motion is something that most probably you covered in high school. For some classes, probably they have to skip it. I don't know. Okay. I'm going to start discussing what is URM, or uniform rectilinear motion. Probably you can guess. Let me just make this a bit smaller. I don't want it to be hidden by our chat box. Yes. So anything you know from uniform rectilinear motion, go ahead. Uniform rectilinear motion, what does it mean?
Constant velocity and zero acceleration.
Okay, constant velocity And you're saying 0 acceleration. Anyone would like to say anything? Anything to add? All right. Do you know how to relate some parameters?
Velocity is distance over time.
Okay, so you're saying velocity is distance over time. I hate to use this term because this is basically an average velocity. Since the velocity is constant, yes, I can use it again. However, I would like us to discuss position and initial position and so on. Let me pick a bigger pen. So it's gonna be my actual position, that is my velocity times time, and you can add it to your initial position if your initial position is not 0. I'm gonna say that V is constant, your terms, and the acceleration is 0. Okay, now I want us to plot the xt graph and the vt graph. I'm gonna skip the at graph because it's not important, the acceleration is 0. So how do you think the vt graph looks like? Straight line, increasing, decreasing, curve.
The VT is a horizontal line.
Yes, V is constant. Exactly. It could be negative if you want to. What about the xt graph?
It's a slope, يعني طالع, like a straight slope.
It is a straight line. It could have a y-intercept. So this is the y-intercept. It could be 0 or not. And this is the slope. The slope is constant. If the slope is positive, you're going to have a positive slope. Otherwise, it's going to be a negative slope. I'm going to take it random. So that's for the uniform rectilinear motion. And we actually covered this a bit when we did lab 1. And you were going over the graphs, and you had a template to follow, right? Okay, now we're gonna review what is UARM. Let me save as this document to keep, and let me make sure not to lose it because I'm saving on something old. I'm gonna call it edited. Okay. All right, now UARM, uniformly accelerated linear motion. How do you explain it and how do you describe it? I advise everybody to say something. I can say Michelle is talking. Is that you?
Yes.
Okay. The others, if you're too shy to talk, you can type in the chat. And it's okay to do mistakes. I'm not assessing you. Yes, Michelle, you were saying.
UARM is constant acceleration.
So acceleration is constant. What else?
Do you want to know the formulas for it?
Why not? Formulas,
okay, so we have V is equal to AT plus V0 in this case.
Okay.
And we can also find the displacement. Delta X is equal to half AT squared plus V0T.
Okay. Can I assume that everyone with us, we are 7, everybody knows this, or this is totally Chinese?
I think everyone knows this. We're all in the same physics class and we've already learned this.
Exactly. And like you don't find, it's not new, like you never found them difficult, right?
No.
Let's do the XT, the VT, and the AT. I'm glad we're reviewing this because I need to apply it in projectile motion. Michelle, you tell me, do you think we're gonna, did you do a projectile motion in class as well?
Yes, we started it like maybe end of last week.
Okay, perfect. So this is gonna be like super easy for you. Now, acceleration, you told me it's constant. I'm gonna draw constant. Velocity, how would you draw it?
A sloped line, a straight line.
So y-intercept, constant slope. I'm gonna do this. This is V0, the y-intercept, and the slope is actually A. What about the xt graph? It's half AT squared. So it's in T squared. How does it look like? Is it a straight line or not?
A parabola?
It has to be a T squared function. A could be positive or negative. If it's positive, the T squared is gonna be convex, looking at the sky. If A is negative, it's gonna be concave, looking at the ground. So I'm gonna randomly say this. Assuming this is x0, and this will be related to half AT squared plus V0T. Anyway, now projectile motion is made of two separate motions, separate, like independent. One along the X and one along the Y. And the best way to be able to see it is the shadow on the floor and the shadow on the wall. And I love cartoons for that, because when Tom was actually running away from the bomb, we could see the shadow on the floor of the bomb, right? So a lot of physics can be shown, and some physics are wrongly shown in cartoon videos. I don't know if you know what I'm talking about. Anyway, what is projectile motion? Projectile motion is when you have a certain object fired at an angle different than 90, because 90 degrees or negative 90 degrees is gonna fall under the chapter of free fall. So if I take this example where you have any angle, this is projectile motion. This is an angle theta. If theta is equal to 0, you're gonna also have projectile motion. If theta is negative, you will also be having projectile motion. So theta negative means this is my new theta. Okay, so all these are called projectile motion. The only thing you should be aware of, always start your projectile motion from the origin. In other words, if you have, let's say, a long building and Superman is jumping from the top of the building, please take your axis to start from the starting point of the jump. Otherwise, all the equations we're gonna write now will not be applicable. I'm gonna take x0 to be 0 and y0 to be 0, okay? Just to make my equations a little bit simple, okay? Yes, this is our next slide. I'm gonna add one more slide because I think we need it to discuss a bit the X and the Y. I'm gonna say the X motion alone, okay? And this is the Y motion alone. I'm gonna repeat Michelle's words by saying for the X is gonna be VT, right?
Yes.
And for the Y, it's gonna be, half AT squared plus VT, V initial T. Okay, V initial T. I'm gonna call this V initial, but it doesn't matter because V initial and V final are the same for the X motion. Probably I should remind people that this is gonna be URM and this is gonna be UARM. And now I'm gonna ask someone like Giorgio. Giorgio, how come I have UARM for the Y and URM for the X? And not the opposite?
Because the Y is varying in projectile and the X is constant.
Exactly, but why? How come the Y is varying? X is not constant, it's varying uniformly. But why?
Vy always changes, whereas Vx is constant.
Yes, this is so true. So in other words, I'm gonna type it here. I'm gonna say that the motion along X is uniform, right? And I'm gonna copy paste the same statement to say the motion along Y is accelerated. And my question is why? Probably Magali can add to you. So Magali, why do you think the motion along X is uniform and the motion along Y is accelerated? Why? Why not the opposite? It is due to something?
We can see in the equation also. No, it's not the same.
Okay. The equation is
along the x-axis, no forces are acting, but along the y, there's the force of gravity. That's why we use the value 9.8.
Yes, yes. Selena is saying because object falls on the y-axis, she means gravity. And Giorgio saying due to gravity. Exactly. So if I start, let me see if my green pen write nicely here. If I start from Newton's second law, sigma F equals ma, the only force acting on my system is the force of gravity. So I'm going to have force of gravity to be equal to ma. And you know force of gravity is m times g to be equal to ma. So I'm going to end up, and this is a vector equation, vector equation, vector equation, vector equation. I'm going to end up saying the acceleration is equal to gravity, exactly like in free fall. And you know, vector gravity is always vertical down, vertical along y. That's why I don't have acceleration along x. So the acceleration here must be 0 because I don't have gravity along the x-axis. And this one should be replaced by -10. I'm going to take negative for downward. Fine. Another question. Back to Giorgio, or probably talk to Selena. And Selena, you can answer in the chat or you can unmute yourself. Selena, we're saying V initial and V initial. Are we talking about the same V initial?
Yes.
It is basically the same V initial somehow, but for the X motion, I'm going to take only the X component of V initial. And for the Y motion, I'm going to take, so they're not equal in value. And in our next slide, I'm going to discuss the initial velocity, okay?
The same initial velocity, but it's divided into Y component and the X component.
Exactly,
That's
so they
I
have
mean.
something in common, exactly. Let me call them VIX and VIY, all right? I'm going to continue now. There's nothing else to say here. However, I can write, if you want, I can say the Vx along y is going to always be equal to the initial value of it. It's not going to change. It's constant, no acceleration. However, the Vx is going to be varying as AT plus V initial y, okay? As long as you take A to be -10, okay? And let me separate this mess from our equation. Okay, so let me move to the fact. I'm gonna go back to this one, by the way, but now let me move to the fact, what is V initial X? I'm gonna start by drawing the X and Y axis. V initial is vector, and I wish more students would join us. Anjad, this is very important. So V initial is vector velocity at the first second of the motion. This is the launching velocity. And theta will be the angle with the x-axis always. So I should start by drawing the y component, the x component. This is the x component. I'm going to call it VIX. And change the color a bit. Let's see if pink looks nice. And this is the y component. Okay. Now, if you follow SOHCAHTOA, you know that the x component is the adjacent or the opposite. The x is the adjacent, right? Yes, all right, Joe. So Joe, I think it's gonna be great next time to sign in from the lab. However, Ms. Jinan is not available in the lab after 4:30. That was my struggle. I'm sorry for that, but Joe, we're recording the session, so probably you can watch it again if you need. Probably you don't need. All right, so VIX, is it adjacent to theta or opposite to theta? Help me up.
Adjacent.
It is adjacent. So I'm going to use cosine. So it's going to be the V initial itself, cosine theta. So you should calculate V initial X first. And VIY, is it the adjacent or the opposite? Yes, because theta is looking at VIY. So I'm going to use sine for it, okay? Hopefully, I know all students struggle with components. I don't know about you. So you're supposed to calculate VIX and VIY before you start the projectile motion. Now our experiment, we need to launch, and I'm going to show you the experiment in a bit. And I think I did not close it. Yes, it's still here. So I'm going to show you that we're going to vary some parameters. We're going to keep some parameters constant, and we have some measurements to do. And the measurement that we're going to do is only one. It's the range. This is the value that we're going to look for. Let me start by defining what range is. And then I'm going to go over the theory to tell you what is the equation for range, because you're supposed to know how to derive the equation for range. And I'm going to start showing you the equipment, the experiment, the procedure, and that will be it, okay? So the range by definition is the distance between the starting point which is here, and the landing point. So you're gonna get a big ruler and you're gonna measure the distance from the launching point to the landing point, and you're gonna call it big R. Okay? Now my question is, and probably I can show you in the lab report, this is the manual. So this is the launching and this is the landing. And here they call it S, the range S. You can call it R. And this is the equation for the range. And my question is, who can try to derive this equation? Where did we get this equation from? Have you ever saw it before? Anyone?
Yes,
Can you
We
help
did
me?
it in the physics course.
Let me
we-
see. Isn't it the first question? For what? Fill, they don't ask you how to do it, but we need deduce the angle, sketch a graph. All right, so how do we find it? Help me, Michelle. And the others, type in the chat anything you remember. You're too quiet for me. I missed you. So how do we find R?
So first of all, we can use the equation delta y is equal to half AT squared plus V0 YT. And since we're going from the initial position back to the same initial height, then delta y is going to be equal to 0. So then we replace.
Okay, I want to stop you, Michelle. So Michelle is saying that we're gonna take at this point y is equal to 0. By the way, as you can see, I'm not writing delta y because I already assumed that my initial y is 0. All right, and I can see that Andrew just joined us. Hello, Andrew. Talk to me. I don't know if you can hear me. Anyway, yes, Michelle. So the first statement you said is y is 0. Continue. Then what?
Then after that, we can see that it isn't in terms of t. So we replace t with delta x over v0 x, and we can assume x0 is 0. So then it's just x over v0 x, and we switch it all around.
All right. So the range basically is nothing but the value of x. In other words, what would be x for us to have y is equal to 0? So if I replace y is equal to 0, I will end up with half AT squared plus v initial t and v initial yt. And for you to be able to solve for the time, to be honest, to find x, let me change the width of the pen. To find x, you need v initial x times time. So you need the time. And I'm gonna find the time from the blue equation. You see, you have t squared, and you'll end up with two values for time because y is equal to 0 also at the origin, at the beginning of the motion, at the start of the motion. So for t is equal to 0, you're gonna have 0. And for t is equal later on, you're gonna also have 0. So in other words, I'm gonna do, this is 0 equals to t into half AT plus v initial y, right? And you take this to be equal to 0 to find t, and then you replace t in here, you will end up with this equation. So this equation is x if you replace t by this value. Probably I can tell you what it is. It is negative VIY divided by half a. Okay? Don't forget that a is negative g. That's why the negative and the negative are gonna cancel out. Okay? And don't forget that VIX and VIY are written here. So in other words, VI and VI will cancel out. Cosine and sine will turn into something else. And this is why you will end up with sine 2 theta. Remember, sine 2 theta is 2 sine theta cosine theta. So this is where the sine and the cosine will eventually be hiding. All right? I just wanted to have an idea where to find the range from, but under no condition you need to derive it for the lab report as you see it. All right? Now some questions using common sense. And the question is for Joe, and Joe can answer in the chat because his microphone is not functioning. Joe, I've asked some of my classes, not yours, if you ever shoot in your daily life. I mean, by shooting, it doesn't have to be a gun. It could be anything projectile motion. So my question for you, everyone in the class, and specifically Joe, is any projectile motion you do in your daily life? Let's see. So everybody in the chat writes something about it. So projectile motion from daily life. Come on, I can give you like millions of examples. Michelle, Selena, Magali, Andrew, Giorgio, Nassim. Hello, Nassim. I want you to give me examples of projectile motion in daily life. Throwing it. Thank you so much. Basketball playing. Anything else? Jumping in the pool. These are not perfect projectile motion with no air resistance, but they are projectile motion with air resistance. Jumping in the pool. What else? Thank you for throwing anything trash in the bin. Throwing. Or probably socks in the laundry. Throwing socks in the laundry. All right, anyway, why am I a frog? All right, so the frog is actually jumping and throwing a baseball. Yes. Mike, why am I asking you this? Throwing a baseball. I'm asking you this because basically, you know from daily experiences that some angles would give you farther ranges, like higher range, greater range. So I'm going to ask you now next, which angle you believe will give you the greatest R as in range? I'm sure you have exactly, but why? You never throw at 90 degrees, neither 80, and you never throw at 30. 30 is too low, it's gonna fall down quickly. 90 is too high, it's gonna fall back on your head. But 45 is exactly in the middle, and it's gonna give you the greatest range. Now, if I take the formula of range, if you need to do it mathematically, can you unmute yourself and tell me how come 45 degrees is gonna give you the greatest range? So theta 45 degrees, how does it give you the greatest range? Anyone? Thank you, Andrew. Andrew, can you unmute yourself? Please, I need to talk to you. Okay. Can I talk to you, Andrew? Okay, you are at the library. All right. Fine, no problem. Can I talk to Giorgio a bit?
Yes, Miss.
Okay. Giorgio, I'm gonna break down the question for you into small steps. Yes, Selena. Back to you, Selena, in a minute. Giorgio, the sine function varies between two values. What is the maximum value a sine function can have?
1.
Exactly, it cannot be more than that. So for R to be maximum, sine alpha should be equal to 1. Now, can you tell me for which alpha sine will be equal to 1? Let me try on my calculator. It's either sine 0
90.
or sine 90. If I do sine 90, I get 1. I don't know if you can see my screen. So basically alpha, it's gonna be 90 degrees. So the value under the parenthesis should be 90 degrees. Now back to you, Giorgio. If 2 theta is equal to 90 degrees, what would be theta?
45.
Exactly. And this is the proof why an angle of 45 degrees will give you a maximum sine, which would give you a maximum range. So now, Andrew, you know why 45 degrees would give you the maximum range. I know for a fact that from experience, you knew the answer, but you don't know why. Okay? All right, we're gonna study this. Let me try to sketch what we have in the experiment. So we're done with the theory. Now for the experiment, and we're gonna do this next week. I hope I'm gonna be given permission to come to the campus. You have a launcher, like a gun, okay? How about I show you the video directly? It's on YouTube. I don't have the actual raw video. I deleted it. Okay, this is me in the lab or in the neighboring room next to the lab because the lab was busy with students. And the voice is not great because it has a lot of echoes. I'm really sorry for that. It was recorded with my poor iPhone, so it was not great. And I made sure it's so short because I'm sure you don't want to watch a long video. I'm gonna scroll through it, okay? Probably take a screenshot to explain what we have before we watch the video. So probably I'm gonna insert the picture here, so it's gonna be much easier. Just a second, waiting for the screenshot. Where is it? Is it? It's here. It's easier on the screenshot. So what we have, let me crop it so I can make it a bit bigger. And I care about the measuring tools. Let me show you. You see, this is a gun. You see the gun? Let me use this. So this is the gun. You see it here? It's basically, I'm gonna zoom in a bit and hopefully I can show it to you next week. Here you have a spring. And here you have a launcher, like you're gonna press or pull out the trigger, put the ball and release. And it's gonna be so loud, you're gonna have a headache after 30 minutes of launching the ball, trust me. And it's gonna launch like this to fall down on a bench. You make sure that the height of the bench and the gun are at the same height. Otherwise, you're supposed to put the bench a bit lower or a bit higher. Remember, my x-axis and y-axis should start where the launching is gonna happen. Also, you can vary the angle of the launching easily. So you can have 30 degrees, 40 degrees, 60 degrees, and so on, okay? What do you have on this desk? You have white papers, on top of which you have carbon papers. And carbon papers are gonna give you blue dots on the white paper, okay? So every time you launch, it's gonna land on the dark blue paper. You're gonna remove it by your hand and you're gonna find a spot, a blue spot, which is the landing point. And then you're gonna grab this ruler. This is a ruler probably that you never used before, but you're gonna see it next week. It is a regular ruler, but it's written millimeters, not centimeters. But what can I say it? The uncertainty is the same. Look at the smallest subdivision divided by 2. It's gonna be 1 millimeter divided by 2. So it's like a regular ruler. But it's a very long ruler. It's 1 meter long. You're gonna use it to measure the range, which is the distance between the initial point, the launching point, and the landing point. So I don't care where the table is as long as the table is gonna catch the ball, okay? And this is what I'm gonna measure, and I'm gonna call this the range. Now, what do I vary and what do I measure? You tell me from what you understood or what you can guess. What are the variables?
The angle.
Okay, so I'm gonna vary the angle theta. I will also vary the initial speed because I have 3 triggers. Like I can trigger to the first spring or second spring or third. The third spring is very, very stiff. Like you have to pull a lot to be able to reach it. Okay, so this is the initial speed. Okay, you have a timer in here. I don't know if you can see something in red. It's a digital timer. You see something in red. Some of the benches I have, the bench is destroyed because it's so loud and it's gonna create a lot of vibration that we destroyed some of the benches. The timer is not functioning properly, but the timer is gonna give you the initial speed. And I know the initial speed, I have them written, so I'm gonna give them to you. Some of the benches will not be able to measure the initial speed, but it's known from the catalog and it's not a big deal. And you can know V1, V2, V3 by order of magnitude. Like V1 is the first trigger, V2 the second, and V3 the third. And what are we gonna measure? So we vary those two and we measure. What's the purpose
We
of the
measure
lab?
the time and the distance x.
We're only measuring the range. You can call it the distance x. Be careful, it's the distance between the launching and the landing, okay? We're not gonna measure the time. The timer is only to give me a short time inside the gun. So it's the initial speed. And it's gonna give me the value in meter per second directly, not seconds. So we cannot measure the time unless you have a slow motion video and an actual timer to give you the time, or a sensor or something. It's gonna be so fast, we're not gonna measure the time, okay? Now back to your lab report. This is your lab report, question number 1. For what launching angle would you expect a maximum range? Explain, we just did it. So you can copy the answer. Launching velocity V1, V2, V3, the angle, you're supposed to vary one variable at a time. So you keep V1 constant, you vary the angle. We're not gonna do 0, we're not gonna do 90. So when I give you the lab report, I'm gonna remove this because 0 is gonna give you nothing. It's gonna hit the table. 90 is gonna fall back down on the gun. So we're gonna remove those. You vary the angle for each, and you're gonna see how the range varies according to V1, V2, V3, and how it's gonna vary according to theta 1 to theta, I don't know, 2, 3, 4, 5, 6, 7, 8 values. Then they want you to draw the 3 plots on the same graph. This is a bit tricky on Excel if you don't know how to do different plots on the same graph. However, if you struggle with this, just do 3 different graphs. And these are graphs X and Y. All right, this is not clear. I'm gonna say range as a function of theta. They never tell you, okay? This is a draft. I'm gonna send you an actual lab report. So 3 plots, meaning 1 plot for V1, 1 plot for V2, and 1 plot for V3. Deduce the angle corresponding to the greatest range. You're gonna notice that 45 degrees is gonna give you the greatest range. Probably not. It depends on the errors you have in your experiment. Some students may have some values a bit off. Deduce the angle on done. Sketch a graph of your projectile showing horizontal and vertical. Let me explain exactly what they want because you're gonna struggle with this. You're gonna draw pen. Yeah, you're gonna draw the projectile motion. Okay, let me do it here so at least we can keep it. I'm gonna insert a new slide. Okay, so this is X and this is Y, X and Y. And this is projectile motion. You are asked to draw the velocity vector at every point. Okay, Andrew cannot talk. Joe cannot talk. Magali, can I talk to you? No? Selena, can I talk to you? We have 2 Selenas. Any Selena can talk?
I can talk.
Yes. Selena.
Okay.
Selena,
Yes.
just help me a bit. You know, the velocity vector is gonna be like this. It's always tangent to the motion. Am I right?
Yes.
We don't need the velocity vector. We need the X and Y components of it. We know that the X component will always be VIX. So it's not gonna change. There's no time component in this one. This is a constant that I'm gonna call K. However, the Y component is gonna vary according to -5 T plus V initial. Why -5? I assume half A is -5. Do you agree? This is an estimation because A is not exactly 10. So -10 over 2.
Okay.
All right. How can I draw the velocity vector at point A, at point B, and at point C? And later on, I'm going to do D and E with someone else. Let's start at B. How is the velocity at B if B is the top of the motion? Is it vertical, horizontal, or at a certain angle?
Velocity here is 0.
The Y component is 0. So I'm going to
Yes.
say at this point, Vy is going to be 0. However, Vx cannot be equal to 0 because Vx is a constant K. Okay?
Yes.
So if the Y component is 0 and the X component is not 0, it means that the velocity is going to be horizontal. So this is the velocity vector. I'm gonna call it V. Okay, can we try A?
Okay. A.
Can I say that Vx is not gonna change?
Yes, it's a constant.
Okay, I'm gonna draw Vx same everywhere. How about we do those as well? So I'm gonna say Vx here is the same, Vx here is the same, Vx here is the same. I mean same length. This has to be a bit longer. So those, I'm gonna call them Vx1 and Vx2 and Vx3 and Vx4 and Vx5. They're not gonna change. They're gonna be exactly the same length. Now in green, Vy is gonna be initially high. This is Vy. And here, do you think it's gonna be the same or shorter or longer?
Longer.
As you go up, gravity is gonna pull you down. It's gonna slow you down.
So shorter.
Yes, it's gonna be a bit shorter. This is Vy. And here Vy is 0 because you stop. The Vy is gonna stop. And then what happens here? It's gonna be up or down, Vy?
Down.
Down, because it's gonna come back down. And if I take V1 at this spot, will it be longer or shorter than the previous one, Vy? Say it again.
Longer.
Yes, because due to gravity, you're speeding up downwards. Now the velocity vector, I need a very sharp pen. Let me see this one. Okay, the velocity vector is the resultant of Vx and Vy. So it's gonna be like this. This is the V vector. The V vector is this because you don't have a Vy. And here V vector. So you guys, you know the V vector. Now you know that V vector is broken down into two components. The blue component and the green component. The blue component is actually the same all the time because there's no acceleration along X. The green component starts very long and it's gonna shrink until it reaches 0, and then it's gonna increase in size again. Okay, and this is related very closely to the last question in the lab report. The last slide is only the YouTube for the experiment. So next time I see you, I'm not gonna explain the whole thing again. I'm not gonna show you any procedure. You can start immediately. Fine. I'm gonna send this to you, and you can view the YouTube from it. The lab report, you don't need it for the moment because you don't have values. You need to wait until you go to the lab, hopefully next Monday, to do the experiment. And that's it. And please meet with me anytime you want. If you have some questions related to previous stuff. I know, Nassim, for a fact, you need to meet with me. Am I right?
Yes.
Okay, Nassim, we just need to decide on a meeting time. Okay, before you leave, some students, hopefully they're here, are not done yet with classwork 2. Yes, sir. And yesterday you told me he's not even attending the course, right? Thank you, Joe, for submitting classwork 2. What about Bodwin and Andrew? I already talked to Bodwin, but what about Andrew? Andrew, what's wrong with classwork 2? You told me you have no problem with it, right? Talking to Andrew. Earth is calling Andrew. All right, if Andrew cannot respond, I'm gonna email him. I don't know if he can hear me. Andrew, I just want to make sure your lab 1 is okay, because it seems that it's not there yet. It shows that you're still not completing. Okay. And let me know about classwork 2. Okay. Anyway, I'm gonna see you next week. Thank you for today. I'm gonna stop